Alright, here we go again. Yet another video in my series about my esoteric programming language Funciton. Now, in a previous video I emphasized that the only data type that Funciton knows is integers, although it's arbitrary size integers. But then in the previous video I showed that that doesn't necessarily mean that that is the only data that you can process. You can actually encode strings in integers. Today I want to move on to lists, or arrays as they are sometimes called, in which you can have any number of elements, which can be integers, or they can be strings, because strings are now integers as well. And of course, if we can find a way to encode a list in an integer, and we can put integers into lists, then it means that we can also put lists into lists, and we can nest them arbitrarily deep. You remember our 3 criteria from last video? When we were talking about strings, we wanted the full Unicode range, but then we found that that is still a limited range in which every element can be represented with just 21 bits. We can no longer afford to limit ourselves that way, because now we want the full integer range. We want to be able to represent zeros and negative numbers and any size of number, from negative infinity to positive infinity. Except, of course, infinity itself. As far as the second criterion goes, we still want a simple encoding in the sense that we want to write as little Funciton code as possible. But I gave variable length encodings kind of a hard time last time, but this time we're not gonna get around that. And of course, as before, we want to make sure that the same list with the same elements is still going to be encoded as the same integer. So, let's see if we can come up with an encoding that fits these criteria. So what do we really want to be able to do? We want to be able to take any number of integers, which could consist of arbitrarily many bits each, and we want to be able to cram them into a single integer in such a way that we can still reconstruct what the original integers were, and that we can tell how many there are in it. So one might be tempted to just concatenate them, but then of course we immediately run into a problem. We don't know where each number starts and ends, and so we can't even tell how many numbers there are, much less what they are. Okay, you might think, so why don't we just put some kind of separator in between them that we can recognize? Well, what kind of separator are you going to use? The 0 bit? Or a bit sequence like 1010 or whatever? The problem is that such a separator could always occur in the middle of any one of the numbers that we're trying to put into our list. And then that would cause that number to be split somewhere in the middle where we don't want it and become 2 completely different numbers. So, that plan doesn't work. So even an individual number, we first have to encode in some way. I've already hinted that we're going to need a variable length encoding. Let's start by dividing the number into chunks. We can make these chunks any size that we want. It doesn't really matter what number of bits you use, but since we already used 21 bits for strings, that's what I'm gonna go with. Okay, so now we need to come up with an encoding that will tell us how many chunks there are in the number. How are we gonna do that? Well, maybe we want to put a number at the start in the least significant digits that will tell us how many chunks there are. Can we do that? Well, how many bits do we need in order to encode the number of chunks that we're encoding? Well, our original number is arbitrarily many bits. So how many chunks are there? That's right, it could be arbitrarily many. Which means that the number of bits we need to encode the number that tells us the number of chunks is also arbitrarily many bits. So that won't work either. Well, here is something that does work. We can put a 0 bit in front of every chunk and then put a 1 bit at the end. And that way we can basically follow this chain of 0 bits until we hit the 1 bit, which indicates the end of the number. But remember, we wanted to encode both positive and also negative numbers. So after a finite number of chunks, we still have a finite number of bits. So if the rest of the number is all 0 bits, then it would always be positive or 0. So we're going to add another single bit at the start, which I'm going to call the sign bit, which will indicate that the encoded number is negative. So we follow the chain of zeros up to the 1 bit, and then we count 1 bit more for the sign bit, and then we know exactly where the number ends, and we don't need to rely on the rest of the number being all zeros. Which means that now if we want to encode multiple numbers, we can just concatenate them up, and we will always know where they start and end, and we can always decode them by just retrieving the individual chunks. Alright, now we know the format, let's see if we can construct an algorithm that will encode and decode a number. So let's start with a function that can encode an element and put it at the front of a list. Now remember that the least significant bits are going to contain the first element of the list, so we're going to be shifting the list to the left in order to accommodate the new element. So we're going to write a function which I'm going to call unshift, and it's going to take two arguments, a list, which may or may not be empty, and a number that we want to unshift into the list, in other words, prepend at the start. What we want the function to return is this, assuming that the number consists of two chunks. I also want the function to return the number of bits that it required to encode the number. This will be useful for some later functions. So let's see how the function works on the inside. The first thing we need to worry about is, of course, what if the number is negative? If it is, we're going to do a bitwise not on it, and that will turn it into a non-negative number. And that will tell us the sign bit, which is going to be either 0 or 1. And we're going to put that to the side for later. And now we're going to pass the list and the non-negative number into a private helper function, which is going to encode it chunk by chunk. The first time we pass in the non-negative number, it's going to chop off the lowest 21 bits, and that's going to create our first chunk. Let's put that aside. Then we call the function recursively. So now we have a second invocation of the same function. It will once again chop off a second chunk. And for the sake of this example, let's say that that is the size of the number. So the number now vanishes. In other words, it's 0. So the third time the function calls itself recursively, it will now see that the number is 0. At this point, we know what we want to return. We want to shift a 1 bit into the list, which means that the bit length of that element is 1, because we've created 1 bit so far. And then we return back to the previous recursive call. Then the previous recursive call can just append chunk number 2, and then add the 0 bit that we need to indicate that there is a chunk here. So that means that we've added 22 bits to our encoding, so we're going to add 22 to the number that we're returning. Next, the numbers go up the execution chain again, and we can just append chunk number 1, which once again needs to be preceded by a 0 bit, and that means we add another 22 bits to the bit length. And now, when that function returns, we are now back in the main function, the one that didn't chop off a chunk, but rather remembered what the sign bit should be. So we can now shift in the sign bit, and then we only need to add +1 to the bit length, and then return that. And hey presto, we get exactly what we wanted. Now let me quickly apply a little performance optimization. You see, we always have the 1 bit that indicates the end of the sequence of chunks, and we will always have a sign bit, so there will always be those 2 bits no matter what. So instead of adding 1 to the bit length at the end, we can actually just start with the number 2. And that will save us 1 increment, and we still get the right answer. Let's start with the private helper function. It needs to return 2 things, the list after encoding, and the bit length. Both of them depend on the terminating condition, so let's put 2 question marks here. Now, if n is 0, then the bit length, we've decided we're going to return 2. Whereas for the list, we need to shift the list left by 1 bit, and then use bitwise OR to add the 1 bit. So let's write the bitwise OR first. And then let's write the shift left that will shift the list. And then of course the 1 bit. Now we can conveniently reuse the 1 box here. Now if n is not 0, we need to do the recursive call and then use the results from that. So let's draw the recursive call box. Now in the case of the bit length, we only need to add 22. Whereas for the list, we need to actually shift it left by 22 bits and then do a bitwise OR with the chunk, which we also need to shift left by 1 bit. Now the chunk is of course the least significant 21 bits of our input number, so we're going to use our magic number and a bitwise AND to extract that. Now the value that goes into the recursive call is of course not n itself. We need to chop off these 21 bits that we just extracted from n, so it's actually n shift right 21, which again I'm going to write as shift left negative 21. Now let's rearrange some of this to make some space. Now, in order to join up all the ends and the lists with the declaration box, I'm going to need 1 wire crossing function, so I'm quickly going to insert that. And now let's connect up all the occurrences of list, of which there are only 2. And finally, join up all of the ends. Now, the main function is obviously going to need to call this private function, so let's start with the call for that, because we're going to need to deal with the return values from it. On the bottom of this box, the new list is going to come out, but we still need to shift it left by 1 bit in order to insert the sign bit. Now, inserting the sign bit is a matter of a bitwise OR, so let's quickly do that. And what we bitwise OR with depends on whether the number was negative or not, so let's put a question mark box here. Now, if n is in fact less than 0, we need to bitwise OR with 1, otherwise 0. Now, our non-negative number, of course, also depends on whether n less than 0. If it is less than 0, then we need to bitwise negate it. Now there's only one occurrence of list, so we can easily place the declaration box. Now, of course, I don't want to do the n less than 0 twice, but in order to join them up, I need to cross them with the n. So I'm inserting a wire crossing function right now to address that. Now remember that the bit length is already correctly calculated by the recursive function, so whatever comes out of this function is already correct and we don't need to do anything with it, just return it. And there we go, we now have a function that can add an element to the beginning of the list and also tell us the length in bits of the encoded form. Alright, let's finish this off with a function that will only return the new list and not the bit length, which will be useful for cases where we just don't need the bit length. Okay, now let's look at the opposite function, the shift function. This function will take only one input, which is a list, which we presume to contain at least one element, and we want to return three things: the list with that element removed, so the rest of the list, the number that we just decoded, and the bit length of that number. So as we pass the list into the main function, it will take a look at the least significant bit, that's the sign bit, and it'll put that to the side. And then it'll pass the rest of that list into this private helper function, which will now decode the number chunk by chunk. So the first invocation of the recursive function will look at the least significant bit and find that it's a 0 bit, which means that there is a chunk here. So we need to shift out the 0 bit and then remember the chunk for later. The second invocation does exactly the same thing. It notices that there is a 0 in the least significant bit, so shifts it out, and then remembers chunk number 2 for later. And then, of course, the third invocation will notice that the least significant bit is actually a 1, which means there is no chunk here. We are done with the decoding. We still need to shift the 1 out, but then we are left with the rest of the list, which we can just return unmodified. But there are two other values we need to return: the decoded number, which so far is 0, and the bit length. Now, just as in the previous example, we already know that there is going to be the 1 bit and the sign bit, so we're just going to return 2 now. And then, of course, the number is passed up to the previous invocation, which remembers that chunk number 2 was there, so shifting it into the 0 number will reconstruct 1/2 of the number. And then, of course, we need to add 22 to the bit count. And then moving up the execution chain, the previous invocation will do the exact same thing with chunk number 1, which will reconstruct our non-negative number. And then we need to add another 22 to the bit length. And finally, returning one more time, we are now back in the main function, which remembered the sign bit. The bit length is already correct, so all we need to do is just use the sign bit to determine whether the number was negative or not, and if so, bitwise negate it, and then we are done. We can just return these values, and that'll give us exactly what we wanted. Alright, this time we have 3 return values, each of which depends on the terminating condition, so we're gonna need 3 question marks to start with. But this time the condition is to look at the least significant bit to see if there is a chunk to process. Let's start with the simple case where the least significant bit is 1 and we know what values we want to return. In the case of the bit length, that is 2. In the case of the decoded element, it's 0. And in the case of the list, all we need to do is shift it right by 1 to shift out the 1 bit and then return the rest. Okay, but what if that least significant bit was 0? Well, in the case of the bit length, all we need to do now is add 22 to the previous bit length that was returned by the recursive call, which we haven't written yet. As for the list, well, we only need to shift that right by 22 bits. In the case of the element, we're gonna need a bitwise OR in order to append the chunk that we're decoding. Now, on one side of that bitwise OR, we want the element from the recursive call, but shifted left by 21 bits. The other side of our bitwise OR is going to be a bitwise AND, because we want to extract the lowest 21 bits from something. And that something is the list, but we need to shift out the 0 bit first, so it's actually the list shift right 1. Now, I almost got myself very confused here because I neglected to label which of these variables come from the recursive call and which ones are the parameters without the recursive call. I'm going to fix that by putting an R in front of those that come from the recursive call. Now let's draw the box for the recursive call. And in every case where the recursive call is made, we always want to pass in the list shifted right by 22, because we only make the recursive call when the least significant bit was 0, which means that we want to get rid of that bit and a chunk. Now there is only one occurrence of our list, our elem and our bit length, so we can easily just join these all up. Next, let's join up all of the occurrences of list and 1, so that we need to implement that only once. And then let's write that bitwise AND. Now I want to rotate that section in the bottom left, because I think it'll fit better if I do. And now only one occurrence of list is trapped, so we only need one wire crossing function. Now let's save some space by moving stuff around a bit. And finally, let's join up all of the occurrences of list. So that's the helper function. Now let's move on to the main function. Now the main function also has one input and 3 outputs, but it doesn't need a question mark on all of them. In fact, 2 of them, the list and the bit length, it can just return directly from the recursive call. It is only the number that we potentially need to negate. So let's start by writing the box for the call to the helper function. Now what goes into the helper function, that's right, the input with the sign bit removed, so we need to do a shift right 1. Now the final extracted element is either the returned element or its bitwise negation, so we need a question mark box to discern those cases. And we do the bitwise negation in the case where list and 1 was not 0. And then let's just implement the bitwise AND. And then we just need a declaration box and join up all of those wires. That one should be a -1. And finally, let's write the function that will return just the list and the extracted element, but not the bit length, in case we don't need that. Now, we need to test this to make sure that it works. So the first thing I want to do is split the standard input into 2 parts, and I'm going to use the comma as a separator. And I'm going to use the single string split function that we wrote in the previous video. After splitting the string, we need to turn each of the substrings into an integer, and then we just feed both of those values into the unshift function. The way I've laid this out, the first integer will be the integer we're adding, and the second will be the list. Now we need to turn both of the integers that we received from the unshift function back into strings. And then I want to concatenate the two, but with something in between. Now, just to differentiate this from the input, I'm going to use the semicolon as the separator. Alright, now let's run that test program on some integers. So we want to add, let's say, the number 47 into an empty list, which is of course 0. And what we get is this number. So first of all, 24 is of course the bit length, which is correct, right? There is one chunk worth of 21 bits, plus the continuation bit, the stop bit, and the sign bit. That gives you 24. The other number is going to be the encoded form of this list. So let's turn that number into binary to see what that looks like. And then if we take that apart, we'll see that there is a 0 bit at the start, which is the sign bit. Then we have the 0 bit for the first chunk. And then the 21 bits that I've highlighted are, of course, the number 47. And then we have the stop bit. Now let's run the same thing on a negative number. Now if I take -48, we should see the exact same bits because that is the bitwise negation of 47. So if I run that, I'll get this number, which you'll see is actually different by only 1. And that is what it should be, because it's exactly the same bit pattern, just with the sign bit changed to a 1, and the sign bit is of course the least significant bit. Now let's take that list and add another number to it. So for example, let's say we want to add the number 2 to that list, and now of course we get an even bigger number, which I'm going to put in my clipboard for later. Now in order to test the shift function, we only need one integer from standard input, but we're going to deal with 3 return values from the shift function. Once again, I'm going to concatenate everything up with semicolons, so we will get 3 numbers with semicolons between them. I forgot to turn the input into an integer. Now if we run that program on the number that we remembered from earlier, we expect to see the number 2 that we added to the list last, because we prepended it to the start and the shift function removes the first element from the list. And now if I take this number, which we've seen before, into that same program, we expect to see the -48, and indeed we do. And of course, the third number here, which is the rest of the list, is now 0 because the list is empty. Another thing that we can see is that if we add the number 0 to an empty list, we actually get a bit length of only 2, which is understandable because we don't need any chunks to encode the number 0, so we will only have the sign bit and the stop bit. The same, of course, is true of the number -1. If we add that, the bit length is still gonna be 2, but the encoded form of the list is now 3, which if I turn that into binary, of course you will see that the sign bit is 1, and then we have the stop bit after that. Perfect! Now we have two primitives that we can use to create all of the list functions that we ever wanted. Everything else we want to do with lists, we can do in terms of those two functions. In fact, we already did something very similar with strings in the previous video, except that we didn't write separate functions for it. The unshift function essentially chops off the first element of a list. We did that with the first character in a string by just doing a shift right 21. And it will also tell you what that element was that we removed, which in the case of strings we did using a bitwise AND with a number consisting of 21 1-bits. And of course the shift function, well, it takes a list and an element and prepends the element to the start. We did that in strings by shifting left the string by 21 bits in order to make room for a new character, and then we used a bitwise OR to add the character. So in all of the string functions that we've already written, we could replace these operations with shift and unshift, and we would get basically the same functions but working on lists. So to demonstrate that, let me quickly show you the reverse function, because I wrote a function to reverse lists as well as one to reverse strings, and you'll find that they are incredibly similar. Now, aside from the fact that in the string reverse function, I used this sort of swirly construct in order to make sure that the old string goes to the right and the new string goes to the left. Whereas in the list reverse function, I just turned the output upside down, which reverses the order of the inputs. But besides that, you can easily see that the shift function, which extracts the first element, is equivalent to the part where we do the bitwise AND with the number consisting of 21 1-bits. And the part that extracts the rest of the list is equivalent to the shift right 21. And of course the unshift function is equivalent to the shift left 21 and the bitwise OR. Apart from that, the two functions are completely identical. We have the exact same recursive call and we have the exact same main function. Cool, so now we can encode literally any list in an integer. But what about the other way around? Like, can any integer be decoded into a list? What happens if I just pick a random integer and pretend that it's a valid list? So what happens if I try to shift an element out of a list represented by the integer 1? Well, let's think about what should happen. The 1 is of course the least significant bit, and that is the sign bit, so that gets shifted out. And now the number is 0. And what happens then? Well, what happens is that it will never find the stop bit. So it should be an infinite loop, shouldn't it? And indeed that is what it is. This will never finish. So I'm just going to cancel it. Okay, so if the missing stop bit was the problem, what about this number? What about a number that consists of a stop bit and then 21 0 bits, and then the continuation bit and a sign bit? Let's convert that number from binary to decimal. Now what happens if we use our shift function to extract an integer from this list? What do you think should happen? Well, what happens, of course, is that we get 0, and the rest of the list is also 0 because the list is now empty. But wait, we already had a valid encoding for a list containing the number 0, and that was 2, right? Because we didn't need any chunks to encode the number 0. So there are two ways to encode the list containing the number 0. Doesn't that violate the third criterion that we had in the beginning of the video? I recognize that this is a matter of philosophy, and my philosophy here is that this encoding, although the shift function will deal with it, the unshift function will never generate this. So if you always use the shift and unshift functions to deal with lists, then this case will never happen, and you will never have this integer representing a list. Okay, what about the reverse? What if I use the unshift function to add an element, let's say the number 47, to something that isn't a valid list? So we now know that the number 1 isn't a valid list. What happens if we add that? Well, we get this number. Let's take a look at this number in binary, and we see the sign bit is 0, the continuation bit, and then we have 21 bits containing the number 47, and then we have the stop bit. And then after that, we have another 1 bit, which is of course the one that we put in. Okay, let's put that number into the shift function to see what it does. And you will see that not only does it successfully extract the number 47 which we put in, but it also correctly reconstructs the value that we pretended was a list. In other words, it isn't at all bothered by the fact that that part isn't a valid list. Okay, what does that mean? Well, that means that we don't necessarily always need to start with the number 0 when we use the unshift function. So if we take literally any number and then we unshift, like let's say 2 elements into it, and then we shift those 2 elements out again, we will always get the original number. So we can treat that number as a third number rather than a list containing the third number. So I would like to call that tuples. So I'm actually going to use the shift and unshift function to do tuples as well. And the main difference, of course, is that with lists, they can be any length, and the shift and unshift function can tell you what the length is by just shifting out until you get 0, the empty list. Whereas a tuple is something where the code already knows how many elements there are in it, and it will always use the shift function only that number of times to extract that number of elements, and then not try to treat the last element as a list. Okay, enough about tuples, let's get back to lists. Now that we have the shift and unshift functions, which are basically the most fundamental primitives in order to construct and deconstruct lists, we can create all sorts of list-based functions. In particular, we can write an indexing function, which will literally just count up an integer while it's shifting elements out of the list, and then we will know where in the list an element is, for example the 5th element, and we will know its bit offset. And once we know its bit offset, well, we can remove an element, insert an element, replace an element, or even extract a sublist, which is the same as substring but for lists. And with a little trick, we can also implement a reverse indexing function, which basically shifts all of the elements out of the list all the way until it reaches the end, and then it starts counting from the innermost recursive call upwards. And that way we can find where, for example, the 5th last element is. And of course, if you look for the 0th last element, well, then you know the bit length of the list, and then you can easily concatenate 2 lists and all sorts of other things. But wait a second, what is this? Okay, it says filter. Okay, so we want to go through a list, look at each element and see if it matches some criterion. So like for example, let's say you want only the even numbers, or you want all of the strings that are not empty. Well, implementing the iteration through the list is easy, but how do you actually specify such a criterion? How do you make a filter function that is general enough that you can specify any criterion? Here's another function that's kind of like that. It's called map. You can use this to turn every element in a list into some other element. For example, if you have a list of strings and you want all of their lengths, right? So you want to call the string length function on every string inside of the list and then construct a new list from that. Again, how do you specify that you want the length of a string? Maybe you want to like append a comma to every string, or maybe it's a list of integers and you want to like double them all. How do you specify that you want to go times 2, or literally anything? Obviously, in a typical programming language, the answer is lambda expressions. But how do we do this in Funciton? Well, let's think about that, and I'll see you in the next video.